Hi, and welcome to this part of the course in which we tackle recursion. You will see that recursion is sometimes used to implement um, an iterative behavior, a repetition behavior, like iterative code, where you have loops. So the difference is that such kind of repetitive behavior can be often better defined with an inductive description, as we already saw in a couple of uh, chapters about induction, summations, and sequences, etc. So in this chapter, we will see um, how recursive or inductive functions, mathematical functions, can reflect this type of behavior. So we'll talk about recursive functions. Um, and then we will see how we can develop algorithms that implement those functions. The behavior, they would actually reflect the behavior of those recursive functions. So we should be able to define them and to trace them to actually know how they would execute at runtime. So it's really important, the second part, so that you can also prove their correctness. Typically, this relates to the proofs by induction. Um, and later on, we will see a couple of interesting examples, just in case you didn't see them, about recursive algorithms, namely the binary search algorithm, um, and later on the merge sorting algorithm, which is really important. Okay, so let's start with the first part. What are recursive definitions, and how do they embed in them a certain repetitive pattern? So a recursive or inductive definition of a function consists of two steps: a basis step, which specifies the value of the function at a certain base case, typically 0, or the first element in the domain. So it could be f of 0 or f of a certain base case. And then a recursive step that gives a rule for finding uh, uh, any value from smaller values, okay, from previous smaller values. And he actually, in this step, we have an established recurrence relation that defines the term, any term with respect to it, to one or more of its previous terms. So typically, in this case, f of n is the same as the sequence a0, a1, up to an, where f of I is a index I. So let's consider a couple of examples. Suppose that f is defined as follows, with the basis step being f of 0 equal to 3, and the inductive step, or the recursive step, being f of n plus 1 equal to 2 times f of n plus 3 for every n greater than 0, or greater than or equal to 1. So in this case, we can find easily f of 1, 2, and any other I with respect to the previous values. So to do so for the first items, and actually f of 1 is can be found using this recursive definition in terms of f of 0, and this definition here. So it's equal to 2 times f of 0 plus a 3. F of 0 happens to be 3, so we can replace it in this arithmetic expression, and we will get 6 plus 3, which is equal to 9. You can do the same for finding f of 2. Now you can use this value while calculating the f of 2, which is the value of f of 1. You can use the value of f1 in calculating the value of, the f of 2 in calculating the value of f of 3, and so on and so forth. So I think you're already familiar with this kind of reasoning or recursive definition of functions. So, and I think you can use this same style to define the factorial of an integer n. So, well, as for the basis case, I think we all agree that f of 0 is equal to 1 by convention. And then, on top of that, the factorial of n, which is n multiplied by n minus 1, multiplied by n minus 2, down to 2 times 1, is clearly equal to the value of n. So when you are computing the factorial of n, it's clearly the value of n multiplied by the factorial of the previous number, which is n minus 1, and which can be similarly recursively defined to be as follows: the value of n minus 1 multiplied by the factorial of n minus 2, and so on and so forth. Okay, so down to 0, where actually finally the factorial of 0 is equal to 1. So yeah, so I think it's quite natural to define it in this way. So factorial of n is equal to n times the factorial of n minus 1. And you will see how we can reflect such recursive definitions using algorithms. Let's consider one last example, maybe the Fibonacci sequence, where the first two items are equal to 0 and 1. And then any item actually in this sequence or any term it's equal to the summation of the two previous terms. Okay, so in case you want to find f of 2 here, so it's equal to the f of 1 plus f of 0, which is finally 1 plus 0, it's equal to 1. F of 3, I think you guessed it already, it's equal to f of 2 plus f of 1, which is finally 1 plus 1, it's equal to 2. And so on. So f of 4 would be equal to 3, then f of 5 is equal to 5, etc. So we can easily calculate these values one after the other. And we will see also an example of a recursive algorithm that reflects this definition. So let's start with those recursive algorithms. An algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem with a smaller input. So we can imagine something like a piece of code, a program or a function, let's call it track, that takes in a certain problem P, and then the let's say the pattern of such recursive functions would be something like the following. If P is the base case, okay, if it is the basis case or the basis step, then return certain literal value, okay, return the certain constant value or literal value, or just solve it actually, okay, so just solve it because you can return a literal value. And otherwise, okay, it's straightforward, like return the obvious result for that basis case. And otherwise, well, actually, you would combine the solution for the sub-problem of P. Okay, so it could be this problem, the sub-problem could be just one instance smaller than the problem P, or it could be half of P, or any other kind of approach to make the input smaller for the next step. So otherwise, we would calculate the we would call the same function the rack, but over a certain sub-problem of P. Okay, SP would be smaller than the problem P itself, the original problem. So it could be of the size of the problem P minus 1, or half of the size of P, or quarter, or any fraction, or anything that makes it actually smaller than the size of the problem P. But it really depends on the nature of the problem and whether it can be solved by cutting the original problem into two halves, or just taking the problem size minus 1, etc. And then we would return actually at the end a certain solution that is the combination of this recursive call with let me use this combination operator. It's not the XOR, it's just a way to combine this recursive call with a certain operation, okay, in a certain way, and eventually with literal values, other literal values, okay? So something obvious that you can do at this base step, and then you can combine the result of the recursive call and then return all this at the end, okay? So just straightforward steps here that do not require any repetition anymore, but the repetition would happen because of these steps here, okay? But maybe one of the many questions of students, how it comes that we can use the same function name twice, okay? So, or how can we use the same function name inside that function? So while we are defining the function itself, we are referring to it, okay? So this may seem a little bit weird for the students. So I totally agree. So let's see how this can be executed without any confusion by the CPU. So let's see a couple of words about this first. For the algorithm to terminate, the instance of the problem must eventually be reduced to some base case, and this is what we have tested for it at the beginning of our recursive algorithm. So for which the solution is known, some literal value or some obvious case. And otherwise, we will see actually that the function has to call itself for a smaller input. And as we'll see, recursive algorithms tend to be much more elegant than iterative algorithms, maybe from a mathematical point of view, because they really reflect the straightforward, error-free kind of definition of the underlying function that is defined by those algorithms. So they are a straightforward translation of those functions. Let's take an example. Let's build a recursive algorithm for computing the factorial of n, where n is a non-negative integer. So the solution is to use the recursive definition of the factorial function, for which the basis step is when n is equal to 0. So if n is equal to 0, we should return the literal value 1. So we know what to return, okay? It's otherwise, for any other value of n, well, we know how to do multiplication, okay? So we can return the multiplication of n by something else, but that something else would be the function itself. So the factorial of n requires to call the factorial, but of n minus 1 before combining that value with the value of n itself. So here we have a straightforward multiplication. This is the operation that we are doing, and we have a little value n here. So both of them are straightforward, but to evaluate the factorial of n minus 1, well, this requires to call the function factorial once again on a smaller value of the input, okay? So here the sub-problem is of size n minus 1, so one step smaller than the original problem, okay? And the base case is really straightforward. We just return a little value. Good. So yeah, we already saw this piece of code in red here. We are just seeing it in a slightly different flavor. It's almost the same. But now let's see how this is possible to run on CPUs. Okay, so imagine that we have this function, we define this function in any high-level programming language, Python, Java, C, name it, just name it. So all of them, they know how to do recursions, how to execute actually recursive codes. And imagine that you have a main function that is calling actually this function, and it's passing the value 4 as its argument, okay? The value of its parameter n here. Yeah, so actually I'm not using this n in this example. Yeah, I'm just passing 4 right away. So it's useless to define this variable. But anyway, just we will correct it in the final version of the slides before uploading them. And then at the end, we capture this value in this variable called fact, and then we are displaying this value on the screen, okay? But the most important part here is to see and to know and to be able to do what I will be doing in a few seconds on your own to actually trace the call of this recursive function. I just want to remind you of what we explained at the beginning of the algorithms chapter. When I told you about the basic instructions that any CPU knows how to execute, such as load from the memory, store to the memory, add to different values, etc. So I still remember that I told you about the jump function. Okay, so we use it. Jump conditionally based on a certain condition is used to implement loops and to implement if statements. But we have also unconditional jumps, which are actually used to make function calls. Okay, so actually the CPU would copy the code of your function somewhere in the memory and would jump to that address of the function. And the return statement, it's kind of a jump back to the next instruction in your main program. Okay, so I would just repeat this part. So just to give you this feeling that there's no mystery that's happening behind the scenes. So you have a certain assembly instruction or low-level instruction that the CPU understands. This would be something like jump to the address something, so the address of a certain memory cell, okay? And this is how function calls are implemented at the low level. So typically the CPU code where you have this function call would jump to the memory segment where you have the code of the factorial function. So if we have here the factorial function implemented at this space of the memory, then the main program at the line number 2 here would jump to this memory address, okay, and start executing here. And the return statement that you have at the end of the factorial function would jump actually. So it's implemented also with a jump instruction, but would jump to the line number 3 of the main program to display the value finally. Okay, so we jump back to the caller of this function. Okay, so I hope that you know this information. Otherwise, just take it for granted. And my intention is just to help you imagine what's happening at the low level of the CPU and why functions are possible at the first place, and how this will help me actually to show you what will happen while executing a recursive function, a function that is calling itself. So let's see the sequel of calls. So first of all, when the main reaches this line here, calling the factorial function, a copy of this code will be made somewhere in the memory, and this code is referring to a certain variable called n, except that at this segment of the code, the value that is loaded in the registers representing n would be the value 4, because this is the argument that is passed to that block of code. So you can imagine, according to the von Neumann model that we have in our computers, CPUs can execute pieces of code existing in the memory, and what you have in the memory is a bunch of lines of code or instructions, plus certain cells dedicated to data, and the code that you have will refer to this data. And the function call, when it's done, it's actually a combination of these two types of memory content, instructions, and pieces of data. So here we have two instructions, actually, the if and the else statement, and the piece of data that is behind them, which is n, happens to be equal to 4 at this moment. Well, actually, the CPU will start executing with the first line and is not equal to 0, so it will jump to this else statement. And then it happens that the code to be executed is to multiply n by a value that the CPU cannot evaluate right away. In order to evaluate that piece of code, the CPU needs to actually make another call in the memory. So it will copy once again the piece of code of the function factorial somewhere in the memory. We call it the heap or the stack. Typically, it's seen as a stack because we cannot, from now on, we cannot directly return to the main program. Okay, this function will return first to its caller, and then it will return to the main program. So they are stacked on top of each other, these calls or function calls, they are stacked on top of each other. So this part of the memory, the stack, is now filled in with a new copy of the code, except that the value that is passed to that code is different now. It's equal to this value here, it's n minus 1. So n here is equal to 4, n minus 1 is equal to 3. This is what is passed to the factorial function here, okay? The first line of code detects that n is not equal to 0 because it's equal to 3, so jumps to the next instruction that would multiply n here is equal to 3 actually, by the factorial of n minus 1, which is the factorial of 2, but this cannot be directly evaluated by the CPU. To evaluate it, the CPU needs to make a copy of the code once again, somewhere in the memory, on top of the stack, and actually will pass 2 to it. So I think you got the idea. So 2 is not equal to 0. We jump to this instruction. Now we have to multiply 2 by a value that we cannot evaluate right away. We need to actually make a new call. In this call, n is equal to 1, which is not equal to 0. So we have to return 1 multiplied by the factorial of 1 minus 1, which is finally it's equal to 0. And in this case, the code knows very well what the CPU must return at this step. So it must return 1. Okay, so good. Now 1 will be the evaluation of this last instruction, and it will be returned to this caller, okay, this instance of the function. As you see, it's a stack, so we cannot directly return to the main. This function call, okay, this function call will return to this one, and this one will return to that one, and so on until they return finally to the main. So when we return 1, the value that was loaded in n is equal to 1. So this function would multiply 1 by 1 and will return it to the caller. So we will get 1 here as the value of the factorial of n minus 1. Finally, when this is evaluated as 1, the multiplication can take place. So we had 2 loaded in n. Now this instance of the function execution can return 2 multiplied by 1. So this returns 2 here. And this will fill in the value of n minus 1 in the caller, which has 3 loaded in n at that a chunk of the memory. So now this instance of the factorial function would return 3 multiplied by 2, which is equal to 6, which will be returned to the first instance of the function, and which will finally return to the caller, which is the main function. It will return the value of 4 times 6, okay, which is 24, and this is what will be loaded here in the fact variable. Okay, so the last return statement would make a jump to this instruction here of the main and would tell the main that fact must be loaded with the value 24. Okay, and this is what will be displayed on the screen. So please pause the video, try to think about it by yourself, or just go back to a few slides ago and watch again this part of the video until you master the art of tracing recursive functions. And what I highly recommend to you is to use a debugger actually, instead of just watching this video, and not even not only this time, but any time you want to, you have a piece of recursive code, or by the way, any piece of code that you have programmed, and you want to know what's happening. So the debugger would help you to go step by step over your instructions, and would also show you the stack trace. So everything that is put in this in the stack of calls between the functions, and would also show you the variables window, or whatever it's called in your debugger, to show you the values of the various variables that you have inside your code. Okay, and this is really cool. So I'm sorry, let's go to the next slide. So in this slide, I will leave the example to you. I will just go very quickly over it. So it's just another example where we are artificially using a recursive function. I would say artificially because maybe you knew it already. In certain math libraries, we have a function called pow that takes in two numbers and would return n to the power m. So it's already programmed for you, but just in case you are asked to program it by hand, then know that you can use a for loop and just put in pow the previous initialize pow to 1 and put in pow the previous value of pow multiplied by n. Okay, but you have to do this n times. Okay, so for I equal 1 to m included. Okay, you have to do this, and finally you will get in pow the final power of n to the power m. Okay, because you would have multiplied n by 1, then by n, then by n times. Okay, so you can do it iteratively in this way using a loop. Okay, but you can also use a recursive function, because at the base step, as here in the iterative function, a to the power 0 is agreed on to be equal to 1, and a n, I'm sorry, so this should be a superscript, is equal to a multiplied by the power of a to the multiplied by a to the power of n minus 1. Okay, so once again, you can easily represent this using a recursive function that calls itself on a smaller instance of the original problem. So you see that here we have two different arguments or parameters to this function. And one of them is kept the same because this is what is required in this problem, but it does not matter because at least this one, which is tested in the base case, is decreased at each time. So we are really considering a sub-problem each time, okay? A smaller problem, anyway. Good. So how to prove the correctness of recursive algorithms? Usually using induction. And this is much easier than what we have done, or let's say it's much more straightforward than what we have done with the iterative algorithms. Okay, so as an example, if we want to prove that the algorithm for computing the powers of real numbers is correct, we can use mathematical induction on the exponent n. Well, as for the basis step, well, this is implemented using a piece of code. So since the piece of code is straightforward and very simple, it's quite easy to show that the basis step, the property holds, which is the power of a to the power n is really a to the power n, okay? As for the inductive step, the inductive hypothesis that we can use is to assume that power of ak is equal to a to the power k, as we know it mathematically, so for all a different than 0. And then using this piece of code, we can prove that actually the power of a comma k plus 1 is equal to ak plus 1. So how this can be done? Well, according to this piece of code, this is equal to a times the power of ak, a comma k, which is equal to a to the power k according to the inductive hypothesis that we have just here. So now, if this is multiplied by a, this would yield a to the power k plus 1. Okay, so you can notice that this is straightforward. So technically, it's crystal clear. It's perfect, and this is one of the let's say the advantages of recursive algorithms. They are quite easy to prove. Okay, their soundness and their correctness is quite easy to prove because they are just a straightforward translation of the sound and agreed on, commonly agreed on mathematical properties. Okay, so you just translate the recursive mathematical definition to a piece of code. It's okay, straightforward, very easy to do. Yet another example, but I will go very quickly over it. So I think you have already seen this example in the programming courses, previous programming courses. So in the base step to calculate the Fibonacci sequence, if n is equal to 0 or to 1, you return that value n. As for the recursive step, for any other n, you would return the summation of fn minus 1 and fn minus 2. Well, I think that while tracing this code, you can notice that you have plenty of values that are computed multiple times. So for example, to compute the Fibonacci of 4, you should sum up the Fibonacci for 3 and for 2. But to compute the Fibonacci for 3, you need to compute the Fibonacci for 2 and for 1. And also to compute the Fibonacci for 2, you need to reach these two cases, okay, 0 and 1. Well, here, this is easy to compute. But as you may have noticed that this subtree of the calculation would be repeated once again on this side, okay? So to avoid repeating these calculations multiple times and to optimize the final code, the final number of times these pieces of code would execute, I think there are plenty of tricks. Maybe you learned one of them, and the very straightforward way is to keep the calculated values in a kind of a history. Okay, so just to use them to avoid recalculating a certain previously calculated f of n. Okay, so yeah, just for those among you who are curious about why to do this, but a straightforward algorithm would be this one and would work perfectly, except that it has a certain high time cost. So two very interesting algorithms that we will see and that would require your attention are the binary search algorithm and most importantly the merge sort algorithm, and then we will be done. So these two algorithms are typical examples of the divide and conquer algorithms. It's a family of algorithms where we divide the problem into smaller instances of the original problem, typically by halving it. And then we conquer the problem using by combining the solutions of these smaller problems and just with a straightforward way. Okay, so I think you already know the iterative version of the binary search algorithm. It was a less efficient version because we would have reduced the scope within which we search for the value. So first of all, it's a search algorithm and it works on arrays, and it requires that the array is already sorted. Okay, so it works on sorted arrays. Okay, since the values are sorted, if we're looking for a certain value x, we can spot this value in the middle. If it is equal to x, then bingo, we are happy. We can return it right away. Otherwise, we have to look in this part of the array or in that part. So if x is greater than that value, then it must be in this half of the array. Otherwise, if it's less than the value in the middle, then it should be in this side of the array. In the iterative version, we would narrow down the sections within which we look for the value until we reach only one element here. Okay, but in this version, the recursive version here, so in all the in the best and the worst cases of the algorithms that we saw earlier, we're doing systematically log of n, okay, iterations. But you can see that with the recursive version here, actually we could do better, okay? But simply we didn't because of the code. So in the recursive version, we will do in the best case a certain big omega of 1, because we will do this. If the value is found at this position, the mid position, then we return the position of the value right away, okay, with one only a constant time, a constant number of instructions. But otherwise, only when the value is not found, then we will actually look at one half or the other of the array, okay? So in the worst case, we will have the same complexity, which is log of n. So let's see this algorithm. The code works almost the same. Let's see the arguments first. So we have a sorted array of n elements, a1 up to an. From the main, calling this function the first time, we should pass here 1 instead of I and n instead of j. But to be able to call this function recursively by itself, we work with two parameters of this function, which are, I would like to call them, instead of I and j, I would like to call them the lower index or the lower limit or the start index maybe, and j to be the upper bound or the upper index or the end index of the section of the array at which we are looking. So at first we are looking at the whole array from 1 to n, and x, I would like to call it the key or the value for which we are searching, okay? Good, so these are the 4 parameters: the array, the start index, the end index at which we are looking, and then the variable that we are looking for. And typically I like to have it as the first parameter, but this is the detail. So how do we proceed? Actually, we spot the middle value. We call it m here. It's equal to I plus j over 2 at any iteration. M would be equal to half kind of I and j, okay? It's kind of the middle of the section of the array that we're looking at. If I is strictly greater than j, it means that we have looked up at the whole array and we didn't find x in it, so this is why we return 0. 0 is not a valid index, and it denotes that the value was not found. I know that already in programming languages, you would return -1 just to denote, because your indices may start at 0. So you return -1 to denote that the value does not exist. Okay, so if it is not the case, as long as I is strictly less than j, so it means we are still looking at a section of at least one element. So I is here, j is there, and we are looking at the middle here, m. I'm sorry for this dash that comes from PowerPoint. Okay, so I is here, j is there, and we are looking here at the middle. So if x is equal to a at the position m, okay, so this is am, then perfect. We return m to be the position of the array item where we found x. Okay, it's really m. It's the index of am. Okay, but if x is different than m, then we will be left with 2 different cases. Either x is less than am or x is greater than am. If x is strictly less than am, it means that it exists in this chunk of the section where we were looking earlier. Okay, so this is why we would adjust j and let it stare at m-1 to start looking from I to m-1 at this first half of the section of the array. Okay, so we call binary search the same function. we passed the same array to it and the same element that we are looking for, okay, they won't change. We are still looking for x within this array. And we keep on the same start index if x is strictly less than m, but we stop at m minus 1. Okay, it's useless to search for x above am, okay, because x is strictly less than am and the array is sorted. So otherwise, if x is strictly greater than am, then we would call binary search starting from m plus 1 and up to j, the previous value of j. So in this case, we would be looking for this part of the array. Okay, so I think you should be familiar with this code. And as I told you, it works in logarithmic time. It's really nice. And I just want you to be able to spot how we can use recursive functions to make this code happen. Once again, it has been done using an iterative code, and there is almost 100% equivalence between what you can write iteratively and what you can write recursively. One last example that really requires your attention, because maybe it's not easy to grasp at the first sight, but it's one of the very famous, well-studied algorithms in the literature. It's an algorithm that makes sorting in something to the order of log of, to the order of n times log of n, instead of doing it with something to the order of n squared. Okay, so I've seen that bubble sort, insertion sort, they are to the order of n squared. So here we are reducing at least one of these of this factor, okay, part of this factor down to n times log of n. So how does this algorithm work? Well, actually, it's another example of the divide and conquer algorithms. It iteratively splits the input list into two sublists of nearly equal size, because if the number of elements in the list is not even, well, it's not a big deal. We can cut it into n over 2 plus 1 and let's say floor plus 1 and then n plus 2 floor, okay? So until each sublist has only one element, okay? So the first step that would like actually to handle the problem in an easy way for smaller input is a very straightforward step. It just splits the list into two sublists of almost equal size, okay, until we reach one element. So we are doing no sorting in this direction, okay? So typically when we go down, okay, decomposing our initial problem, okay? But then when we restitute back the final array out of those very tiny arrays of one element each, this is a step called the merge step, okay? So we merge the two sublists, the pairs of sublists successively into a bigger list, okay, with the elements being sorted in increasing order, okay? So just in case we had this big list, let's say 1, 2, let's say 4, 2, 1, okay? So we'd call the merge sort algorithm over 4 and 2 on one hand, and then 1 on the other hand. So we cannot we cannot actually merge these two lists because we don't know at first how to merge a list that is not sorted, okay? So we would call merge sort once again to split these two lists, this two elements list into two lists of size 1, okay? We will separate 4 and 2, okay? So this is how the first phase of the merge sort would proceed, okay? And then now that we have only one element in each list, we know very well how to merge them, okay, while keeping them very well sorted in increasing order, okay? So for example, we would do a very simple test to check that this element here to the right is less than the element that we have here to the left. Okay, so we would copy this element at the beginning, okay, and then we would copy the other element here to at the end of the merged list. Okay, and then we have to merge the result of merge sort over this list with this list here, okay, which only contains one element. And we would apply the same concept, okay? So this one can be merged with this list of 2 and 4 in the same way. So we start by testing the first element in each list. So it happens that the first elements are 1 and 2. 1 is smaller than 2, so we copy 1 first. Since this list is empty, we can safely copy all the values here, okay? Because there are no elements here that are left to check with them, to check whether the elements to the left-hand side are smaller than them, okay? So this is why we copy 2 here, and then we copy 4 there at this position, and then we will have the array sorted, okay? So we will have a more elaborate example on the next couple of slides. So the process ends when all the sublists have been merged, and the succession of the merged list is represented by typically by a binary tree, as I did here actually on this tiny example. Okay, so let's see how this works on a larger example. So suppose you have all these values to be put in increasing order. The pseudocode that you will see in details on the upcoming slides, it's something like this. So merge sort of a certain list L would return L if L is of size 1. So this is the basis step, okay? Otherwise, if L has more than one element, then we would somehow cut it into 2 halves, the left half and the right half, let's say. Okay, so we call them L1 and L2. And then we will use the procedure, the merger procedure that I told you about, but not on L1 and L2 because they are not sorted, okay? We will call them on the result of the call of the merge sort on L1 and the result of calling merge sort over L2, okay? Which will actually, once again, just return the list if it only contains one element. Well, this element is very easy to merge with another list of one element just by comparing them. Otherwise, we will actually further cut it into halves, okay? So until we reach the very base case where every single element is put separately. So let's see how this works over the example, okay? So I omitted the details of the first if statement, and here we have the 2 instructions where we cut the array into 2 halves. So let's see how this applies. So let's call them line number 1, 2, 3. So line number 1, line number 2, line number 3, line number 4, and line number 5. Okay, so line number 4 and line number 5. Okay. So the line number 1 and 2 would create these 2 sublists, okay? So from this original list, executing line number 1 and line number 2 would give you the following sublists. And then we would like to call merge to at the line number 3, okay? We would like to call the line number 3 for the first time on this list, but after calling line number 4 and line number 5 over these 2 lists. So after calling merge sort over L1 and L2. So this is L1 here, okay, the list number 1, and this is the list number 2. Maybe it's not a great choice for the indices of the lines of code. So let's call them C1, C2, C3, C4, and C5, okay? So we are still having here to execute the piece of code C3, but after calling the line C4 over this one and the line of code C5 after on this list here, okay? So calling merge sort over L1 would consist on cutting it into 2 halves according to the lines of code C1 and C2, okay? So almost of equal size. So this would yield 2 different lists, 8, 2, 4, and 6, 9. Okay, so we're doing no sorting in this direction where we're going down. But and now we're waiting on the line of code C3 once again, but after calling C4 on this one, and C5 over this one. Okay, so we can imagine this is 3.1 and this is 3.2. So the second time we're calling C3 and so on and so forth. I think you got the idea. So we cannot merge sort A24 unless we split it into two halves because the size is not equal to 1. And we cannot call merge 8, 2, and 4 unless we merge sort L1 first. Okay, so we're calling C4 on this one too. Okay, and we shall eventually call C5, which is the same function merge sort, but on the right-hand side. And then we can combine them. Okay, so waiting on C3 for the third time here. Okay. So calling merge sort over 8 and 2 would split it into two different subsets. So here we have to call merge sort, and here we have to call merge sort. But this is quite easy actually. So we can restitute the value now because this call merge sort would return 8 itself, and this call would return 2 itself. Now we have only one value on each side, so we know how to combine them in a sorted way. We make so this is the code of the merge function, okay? So don't forget that we had a C3 number 4 to be executed on this line, and this is what we are doing here. So we're executing the line of code number 3, the merge process, okay? So the merge process of 8 and 2 would check for the right-hand value if it is, or actually for the first value in each array, okay? It would take the smallest one, okay, which is 2, and copy it at the first place, okay? It happens that after copying 2 from this array, it becomes empty. So this is why we can safely copy all the other values from the other array to this side here, okay? And now we get 2 and 8. But at the moment that this merge function returns, okay, from this call here, C3.4, this would return to this function here, okay? The merge sort being called on these two arrays. So this is the result of calling merge sort over 8 and 2. This would return 2 and 8, okay? Now we have to execute the merge sort over the other list, which is 4. Well, this would return actually 4, okay? Because the size of the list 4 is equal to 1. So straightforward, we return 4. And now we are ready to execute the line of code C3, okay, at this stage, C3.3. To merge it, well, we compare these two values, 2 and 4. 2 happens to be smaller, so we copy it. No array is empty at this moment. So we keep going. We compare now the next value with the first value from the other array. It happens that 4 is smaller, so we copy 4 at the second time. And since this array becomes empty after copying 4, so we right away copy 8 and we get it at the right place. Okay, so now we have a sorted array that we know very well how to merge with another array sorted array coming from another side. So when this function's merge finishes and returns, it gives back this result to this function here, okay? This is the result of calling merge sort over 824. It returns 248. Do you see? We cannot execute C3.2. We cannot merge this list 248 with 69 because we have to call merge sort over 69 first. So in the same way, we call merge sort, which would split this into two values, and that they can be actually very easily merged together. Okay, so we compare them and we put the smallest value at the beginning and then the next one. And now we can execute C3.2. Okay, I think you should have a clearer idea now. Okay, so now we have the merge of these two lists. So we copy 2 and 4 first from the first array, and then 6 from the second array, and then 8 from this array. This array becomes empty, so we can copy all the other values, which only consists of 9. And this is actually the result of calling C4 on L1 here. So this is the final result of this call. So now we're already, or I mean that the CPU is ready to call C5, merge sort over L2, which would proceed in the same way. It would cut this into 2 halves, and then would cut this array into 2 halves, and then cut this one into 2 halves, and then would merge them in the right order. So we have 7 and 10, then 1, 7, 10, and that will be merged with the result of sorting 3 and 5, which would give 1, 3, 5, 7, 10. And do you still remember the first occurrence of merge? It hasn't been executed yet, okay? Because we have just finished the call of merge sort on the right-hand side and on the left-hand side of these two arrays, L1 and L2, the original ones. Okay, so C4 is done, C5 is done, and now the line C3 can be executed because we have a function call here. Okay, so now we can merge these two results, and this would end up creating the final sorted array. Okay, so we have the values from 1 up to 10 in the right order, as you could imagine. Okay, so if this is not new for you, if it was boring, I'm really sorry. If this is completely new for you, or if you didn't get certain points, so please pause, review the last 5 minutes or so, and until you master this tracing, or the tracing of this algorithm, actually the merge sort algorithm. Okay, you have all the details in the next slides. And you have the whole tree neatly here, so you can print it out, work on it. But I highly recommend that you start from this node, that you do it on a piece of paper, and then you convince yourself that you are executing your the code correctly. You are able to trace it back again on your own. So you have the details of the code on these slides. So it's almost the same code that I talked about in the previous slide. So we have the merge sort of each sublist, okay, where M actually, so from A1 to AM, and from AM plus 1 up to AN, where M is equal to the floor of N over 2. Okay, so you see it's exactly the same pseudocode that I used on the previous slide. Maybe the new piece of code is the code of the merge function. Okay, so it's worth it to get a look at it. Although we didn't try all the details, so we start with an empty list. And while L1 and L2 are both non-empty, so as long as it's not the case that one of the lists are empty, we remove the smaller of the first elements of L1 and L2 from its list, and we put it at the right end of L. Okay. If this removal makes one of the lists empty, then we remove all the elements from the other list and we append them to the right of L once again. So we append them to the right end of L. Okay, at the end of L. Because they must be the elements that are bigger than all the other elements that have been copied so far. Okay. Well, otherwise, it's not a big deal. We just continue, okay? So we remove the smaller first element from the two lists, okay? And we keep doing this, okay? Until one of the lists is empty, then we copy all of its content, as I told you, to the right end of the result list L, and then we return this list at the end. This merge list would have all the elements of L1 and L2 in increasing order, as long as L1 and L2 are already sorted. And this is why we are splitting the arrays all the way till we get one element on each side. Okay, so the splitting step does not do any sorting. Okay, so we just keep doing this until we reach one element, and then we start merging them together in a sorted way. Okay, good. You have another example that you can check on your own, and I will leave the questions for the live session on Thursday. See you soon, and thank you for watching and listening.